Hello CIS 1400 and welcome to another week. Hopefully the last project went pretty well for you and you're able to get through it without too much problems. But we got another week here where we're going to start talking about searching and sorting algorithms. So as always, if you haven't had a chance to read the chapter on searching and sorting, I would invite you to do so first. And second of all, we're going to jump kind of right into code and logic today instead of working our way through sort of a presentation. So I think at this section it's better to learn by doing than by kind of observing. So I'm going to leave a link in Blackboard to this sorting demo starter file. If you would please download that first and pull it up in a PyCharm, pause the video until you're ready to go, and then code out with me what we're going to go through. So I'll give you a second to do that, and then we'll unpause the video and come right back to it. So when we walk through the video, or through the file here, you're going to see that there's a lot of functions that I have listed here. We're going to go through all of them, whether it's one video or a few videos. I haven't yet decided, but if it is one long video, I'll leave links in the description as to get to certain sorts and search algorithms as we go through. But either way, the file has a bunch of functions in it and a main method that allows us to generate a random list. I have a random list generator function here, and what that'll do is just come up with a random list of values based upon how many values I want, the lowest value I want in the list, and the highest possible value I want in the list. So really all it's doing is generating a random integer and appending it to this list, and it's being passed in and generating my list. And then the main method is telling me to figure out what time it is that I start the process, how I sort the list, and then what time it is after I end the process to figure out the elapsed time. And so you're going to find that some of these sorting algorithms are much more efficient than others, but you will practice quite a few of them throughout your assignment this week. So to kind of get into it, the idea of sorting is to place a list or a grouping of elements in sort of an ascending or descending order. So in order to do that, a lot of times what we have to do is swap two elements from a list. So let's say I've got an element at list at index 0 and an element at index 1, and those two elements are out of order. So what I'd like to do is swap them so that they are in the correct order, and so on and so forth, and continue that process until maybe the entire list is sorted. So sorting a list, okay, requires us to be able to swap values from a list. So what I have here in our starter file is a swap function that we'll use throughout a couple of these different methods that we work with. And in this function, I'm passing in a list, I'm passing an index and a second index that I'd like to swap between. So this is the list of elements that I'd like to complete a swap between index 1 and index 2. Now a full-blown swap is actually pretty simple to do. All I need to do if I want to swap something is I need to hold on to the value that I'm going to reassign first. So I'm going to say temp is equal to my list at index 1, right? And then I'll say something like my list at index 1 is equal to my list at index 2. And now you can kind of see the reason for the temporary variable, because now I have completely lost what was stored in index 1 by doing this. And so that temporary variable is kind of holding on to that for me so that I can complete this last line and say my list at index 2 is equal to now temp. Right? If I didn't have that temporary variable there, then both my list at index 1 and index 2 would be equal to the same thing, because I would be assigning index 2, the value at index 2 to index 1, and then reassigning it back to itself, and that just wouldn't make much of a good swap now, would it? Okay. So now that I've got that able to be done, it's time to start getting into some of these sorting algorithms. First one I want to go through is called a bubble sort. So hopefully you read about the bubble sort in the text. The bubble sort is all about taking values and kind of bubbling them up to the top. So working your way through the list and starting at the very first index, working your way all the way to the last index, and identifying if the adjacent elements as you start working your way through the list are in the right order. And if they're not, swap the elements. So let's assume you had a list that looked like this, and we'll say a little comment here. Hashtag, where's my hashtag? And we had a list that had a couple elements like 1, 2, 1, 4, 3. Okay. Now the idea here would be to start making some changes as you kind of go through. So on the first pass, I'll look at these two elements right here, 1 and 2. And I notice that they're in the correct order, so I'm not going to do anything with them. Now I look at these two elements, 2 and 1, I notice they're in the incorrect order. So what I'd like to do is swap them, so now this is 2. And then I can look at these two elements, notice they're in the correct order, so I do nothing. And I look at these two elements, I notice they're in the incorrect order, and so I swap them, 3 and 4. And that's one full pass of a bubble sort. And it just so happens after that first pass, everything is sorted. Had it not been, then what I would do is go through these elements, check to see if they need to be flip-flopped, then go through these, check to see if they need to be flip-flopped, go through these, and check to see if they need to be flip-flopped. But what I wouldn't do is these two again, because I've already gone through this and I've bubbled this one up, and I know it's the largest value. So the actual bubble sort algorithm, if we want to take a quick peek, let's see if it's over here. My bubble sort is in my sorting logic folder. It's going to look something like this, okay? We're going to figure out where we want to be. So I've got a variable called max index, and it's equal to the length of the list minus 1. What that does is it puts max index at the last element in the array. That's as high as I want to go. Okay? As long as the max index is greater than 0, I'm going to come up with another value called index and start it at 0. So this is where I'm actually going to start doing adjacent elements and swapping. And as long as my index is less than max index, I'm going to check to see if they need to get swapped, and if they do, swap them. Otherwise, I'm going to move the index up to 1, and I'm going to keep going through that list, and this is the bubbling factor that's going to allow me to do that. Now, as soon as I'm done bubbling up whatever element I'm trying to bubble up to the very front, I'm going to take the max index and decrease it by 1 so that I don't go up to that last element anymore. It seems kind of silly because I already know that that one's the highest value in the list. So I work my way around, and then I reset the index to 0, and I start going through the bubbling phase again. Okay, so let's go back to our thing and let's see how we can do that. Well, I can actually accomplish that not with while loops. I mean, I could do while loops, but for loops are pretty good. For max index in range of, and we'll say len of my list, right? Because my list is getting passed in. That's the list I want to sort. Okay, the length of my list minus 1. I want to go all the way down to index 0, and I want to decrease it by -1 each time. Okay. All right, and so I want to say for index in range of, okay, max index. So remember, max index is taking on a value from the length of the list minus 1, from the very last index down to 0, okay, not including 0, but down to 0. And index is going to be keeping track of all those bubbling indices. So now index starts at 0 and works its way up to max index. And since max index is decreasing by 1 each time, index is going fewer and fewer values up towards the front each time. Okay? And so now it's time to ask ourselves a question. If my list at at index happens to be greater than my list at index plus 1. That would be the adjacent element. If that's true, what I want to do is then swap the elements from my list at index and index plus 1. Okay. So it's essentially a good bubble sort. And so what I can do is kind of go down to my main method and I can test this if I want. So remember, I've got a thing called rlist. That's a random list of 10 numbers from 0 to 20. Okay. Now I actually have the list getting printed out, and so what I want to do is apply the bubble sort to our list. So what I'm going to do is rlist, actually bubble sort, and rlist. Okay. And if I run this, let's see what happens. Here's the list as it is when it first opens up. So I've got numbers from 10 numbers from 0 to 20. So I've got 5, 6, 9, 4, 16, 6, 16, 13, 0, 13. I started sorting, I ended sorting, and then when it's done sorting, I end up getting 0, 4, 5, 6, 7, everything sorted. And it took very little time. If you notice, it's 2.57 times 10 to the -5th second. So essentially move that decimal place back 5 spots to the left, and that's how fast it took. But if I were to say open it up to say 10,000 elements, okay? I'm going to get rid of the prints just so that we don't have to print things before and after, because that's going to take a while to print our lists. Let's just worry about the time because we already know it works. If I run it again, it starts sorting, and I am still waiting for it to sort. Okay, so notice I haven't gotten to the end sort message yet. So it's still going through and doing this particular method, and then it'll eventually calculate the time. Now if this takes too long, I'll pause the video and bring it back up when it's done. So we'll just have to wait a sec. And there it is. It took 24 seconds to sort 10,000 elements on my computer. Maybe your computer might be a little different when you go through the algorithm. Maybe it's a little bit more powerful than mine. I am working off a very old Mac, but it still works just fine. But there you go. 10,000 elements on a bubble sort isn't all that efficient, and you can think that 10,000 elements, especially if it's just numbers 0 to 20, not really a lot of data to go through. So the fact that it takes that long is kind of a pain. So there are some better algorithms out there. Let's start looking at some of these other ones, like the insertion sort and the merge sort, or the selection sort. Okay. So let's take a bounce over to the insertion sort algorithm. The insertion sort algorithm is based on the idea that I want to sort the list by inserting the element into its proper location into what I have already deemed a sorted subsection of the list. So what you can think of is, if we go through the list an element at a time and kind of grow it into sort of this sub-list. So let's say I've got a list of like 20 elements. Well, I look at, say, the first element. Is it in the right spot? Well, if it's only an element of one, or a list of one element, then of course it's in the right spot. But then when I open it up to 2 elements, I can start looking at those elements, the next element that I introduced, and seeing, is it in the right spot? And if it isn't, I can iterate over the subsection of the list that I already know to be sorted and put it exactly where it needs to be and move everything else down. So my insertion sort algorithm looks kind of like this. I have this variable, this control variable I set it equal to 1, and as long as I is less than my list, the length of my list, I can go through it. This is keeping track of how many elements I have in my, basically my sorted array, sub-sorted array already. So I've got 1 element in my sub-sorted array. So I get a value, and I pull that value out from my list at I, and I set some other control variable j to I minus 1. This allows me to iterate over this subsection of the list, the overall list, that I already know to be sorted. So j is going to keep track of the index of where I want to maybe insert some things. And now while my j value is greater than 0, and the value at my list is less than what's at j, okay, I want to keep pushing the elements down further to the right from where j is, because I need to make room for where I'm going to insert this new element. And each time I decrease j by 1. So essentially what this loop right here is doing is searching for what location should I insert the value that I know right here to go into the sorted version of the array. And once I find that, okay, and I've moved everything down to the right, I can take the value that I just introduced into the sub-array, into the sub-list, and insert it exactly there. And then I increase I by 1, thus giving me another element in the sorted section that I need to insert there. And if I go through that as many times as necessary, I can finally stop it. Now this may seem like a much more complicated algorithm, and it kind of is, but it's a much more efficient algorithm because there's not as many swaps to be had. If you look at it in the bubble sort, we are making tons and tons of swaps, whereas in this one I only make 1 swap per pass through the major array, because I look for where it needs to go and I put it in the exact right spot each time, instead of making that swap a bunch of different times each time it needs to happen. So let's take a look at what that might look like in code. Okay, so let's get rid of this pass instruction. And for an insertion sort, like I said, I want to come up with a I value. So for I, or index, whatever you want to call it, I'm going to go with I, because it's just a counter at this point, in range of 1 through the length of my list. Okay. Now I need to come up and pull the value from the list at I. So value equals my list at I. That's the value that I'm going to look for where it needs to be inserted. I'm going to come up with a j value. This is my new counter to keep track of where it should get inserted. So j is equal to I minus 1, okay? Because I know it shouldn't go where it currently is, so let's look at the place previous to that. And then we'll go we'll say while, okay, j is greater than or equal to 0, because it could go in the very last place, and my value is still less than my list at j. Okay. If those two things are true, I want to keep pushing the element I'm currently at to the right one spot in the array. So I'm going to go my list at j plus 1 is equal to my list at j. All right. And what I'm going to do is decrease j, take it down by 1. And I'm going to continue to do that. And once this chunk here is finished, then the goal is to insert the value that I pulled out first wherever j left off, okay? Or actually one more than where j left off. So what I'm going to do is my list at j plus 1 is equal to the value, all right? And that's essentially the insertion sort. It goes pretty quick that way. Let's change it and try the insertion sort. So let's back these out so we can see that it's actually working and prove to ourselves that it's working. So let's come up with 10 elements again. Instead of doing a bubble sort, let's do an insertion sort, okay, on our list. And let's give it a go. So if I do that, the insertion sort seems to finish in a relatively similar time on 10 elements as the bubble sort did. Okay, let's bump it up to 10,000 like we did before, and let's get rid of the print statements because we've already proved that it actually sorts the list without any issue. Printing it would be a monster job, so let's just get rid of that. And let's come in here, and it's getting the list. It started the sort, and I'm just waiting for it to end. And we can see that it ended in a far superior time to the bubble sort. 10,000 elements with the bubble sort took 3 times as long, at least on my computer it did. This took 8.5 seconds, whereas the bubble sort took approximately 24.5 seconds. So you can see just by doing that and cutting down on the number of swaps we needed to make, the number of times we actually changed values in the array, it really cut down on the amount of time it took for the entire sorting algorithm to process and do what it needed to do. Okay, so again, to kind of recap in what it's working with, let's say I had like a list that was equal to 1, 4, 2, 3, 5, 6, 3, 1, 2. Okay, what it's doing is essentially saying, okay, let's look at this section. This element is already sorted, so let's look at this section, bring the 4 in. Is the 4 in the right spot? So j is where I'm at, currently 4. I want to see if it belongs both 4 here. So j is still greater than or equal to 0. It's at 0. Is value less than my list at j? Well, the answer is no, so I'm not going to do any of this stuff, and I can insert it at j plus 1, where it's going to stay right there. So now I know that this subsection is sorted. My goal now is to bump up I to 2 and bring it in here. So 2 is what I'm working with. Value is 2, j equals I minus 1, so I'm looking here, while j is greater than 0, and value is less than my list at j. That's true, value is less than my list at j, so what I'm going to do is I'm going to kind of temporarily hold on to this as value, so value equals 2, just so that I know, and what I'm going to do is I'm going to change this to a 4, okay, and I'm going to j minus 1, so now I'm kind of looking back here, okay, I'm down here. And while value is less than my list at j, well, value is not less than my list at j, it's actually greater. So then what am I going to do? I'm going to take j plus 1 and insert value. So now I've got this section completely sorted. Right? Let's move on to where I is here. Pull it out, value becomes 3, right? J becomes I minus 1, so now I'm looking at here. This is true and this is true. Value is less than my list at j, so I'm going to push the 4 up to here. Okay? And then I'm going to bump j down, should this work, and is value less than my list at j? It's not. So guess what? I'm going to insert value at my list at j plus 1, 3. And so you can start to see how now I've got this subsection sorted, and I can start to bring some of these other ones in. Now this one's already in its sorted spot, this one's already in its sorted spot. 3 would become the value again. It would back it up and see if it belongs here. No, so then guess what? This would become a 6. This would then become a 5. This would then become a 4. This would then not become anything because it belongs, it's not less than this, so I would change this then to a 3, and now I've got what I need. And same thing with this 2. 6 would get pushed up here, 5 would get pushed here, 4 would get pushed here, 3 would get pushed here, another 3 would get pushed here, and 2 is no longer, because remember values at 2, 2 is no longer less than 2, so I would replace this with a 2, and now I have a completely sorted list. So that's essentially what the insertion sort is doing. It's looking over a partition of the current list to see that it's already in sorted order and see where we want to put the new value, and just kind of keep moving things off to the right as we go. Okay. So there's your selection sort. The last sort we want to go through is the, that's the insertion sort. The last sort we want to go through is the selection sort. So the selection sort is an algorithm in which it's almost like the bubble sort, but what we're trying to do is find kind of the lowest item in the list first and just put it where it belongs, okay? And we just kind of keep working our way through. But instead of making those swaps multiple times, we only have to make the swap once because we've identified what the lowest value is and where it should go, and we can just swap them out that way. So here I've got a counter I equal to 0, while I is less than my list, the length of my list minus 1, so I'm not going up to the last index exactly. What I do is I keep track of a min index, and what I mean by min index is the index of where the smallest value is and where it should go. Okay, so the smallest value in the list, let's say the smallest value in the list is a 6, okay? I'm keeping track of the index and where it should be. So I set it equal to I temporarily, and I come up with this other counter j equal to I plus 1, one more than whatever I is, so I can start searching from that point on. If, or I should say while j is less than the length of my list, so I can start looping through it, and I start seeing if the item at my list at j is less than my list at min index, and if it is, I replace the min index. So instead of swapping an entire thing, I just kind of change out what the min index is so I can keep track of where that's supposed to be. And I keep running through this little loop here, this inner loop right here, till I figure out where the minimum value is, that where I need to put the smallest value. Okay. Once I have that figured out, I can make the swap that I need to do, and then I can move on one more element in the array because I'm guaranteed to have the smallest value in the first spot. And then I can start looking at, okay, all of the values from index 1 and beyond, and then index 2 and beyond, and index 3 and beyond, and so on and so forth. So essentially what I'm doing is I'm just kind of like grabbing the smallest value and moving it to the front of the array each time. Right? So let's look and see how that kind of codes with the selection sort, so I can select what I need to do. So if I'm looking at this in kind of a algorithmically, let's say I've got a list that's 2, 1, 3, 4, 2, 5. Right? My goal is to figure out where the smallest value should go. So I find the index for the smallest value. So the smallest value's index is right here at index 2. And so my goal is then to pump it and swap these two out. So I'm going to make this a 1 and this a 2. Okay. Then I start searching through the array again. Okay. My min index is right where it needs to be. So I swap it with itself. No big deal. Then I start searching again. Okay, my min index is over here. And so what I want to do is swap these elements. So make this a 2, or make this a 3, and then make this a 2. And then I find my min index is here again, and so I make this the 4, and then this the 3, and then this is the min index, and this is the min index. So I've essentially sorted the array by just kind of pumping things back to where they should go. Right? So here, let's kind of code out what our flowchart said. For I in range of len of my list minus 1, just like we said, it's got to go up to but not include the very last item in the list. Okay. Let's find our min index is equal to I, assuming. Okay. And then we'll start going through all of the values, one more than that. So for j in range of I plus 1 up to the length of my list. So I can get all the way through all the elements. And I need to ask myself if my list at j, so what I'm currently going on, if that happens to be less than my list at min index, then all I want to do is I don't want to swap the values, I just want to set min index equal to j. And that's a really quick and easy thing to do, okay? And now once I get through that entire loop, I've identified where the smallest value in the array is located, and what I want to do is simply swap out the values at I with the value at min index. So let's do that. Swap my list, the value of I, and the value of min index. And that way I've got those two things now flip-flopped. Okay, so let's kind of go through and take a peek. And we'll bring our print statements back in. We'll cut this back down to 10 elements just to show that it's working. And there we go, again, a very similar time on the 10 item list. So here's my original list, and here's my sorted list. Let's bump this back up to 10,000 elements. We'll get rid of the print statements so we don't bog ourselves down with those. And let's sort it. And again, we'll have to wait a few seconds, but it should pop up here pretty quickly. And there we go. Very similar, if not identical, to the insertion sort, because we're making approximately the same amount of swaps. It should have a time that's somewhat similar to that. Okay, so those are the three sorting algorithms that you're going to be held accountable for when it comes time to do the lab. Or the activity. You are going to do one selection sort, one insertion sort, and one bubble sort algorithm on the list that I will give you. There is another sort that I'm going to demo, and I'll probably demo that in a different video, the merge sort, just so that you can see how it goes. And then the next video, I'll have us doing some searching algorithms. So that'll kind of end it for this one, the sorting. I'm going to make everything available to you again, the starter file for this. I will, again, also make the end file for you available, and all of the flowcharts so that you can kind of see the processes they went through. So I'll see you in the next video when we start talking about the merge sort and about the linear and binary search algorithms. Okay, the next algorithm I want to get into is what we call a merge sort. Now, the reason I kind of saved this one for last because it's a very complex algorithm, but it's an extremely efficient algorithm. One of the better ones out there. But what the merge sort algorithm is, it's what we call a recursive algorithm. So it's a function that kind of calls upon itself to break the list down. So here's essentially what's going to happen. Let's say you've got a list and it has a certain number of elements. What we're going to do is continually break that list down into halves, and till we get down to where each half is a list of list size 1. So let's say you've got a list of 10 elements and I break it down to 5 elements and 5 elements. Then I'm going to take each one of those halves and break it down in half again to where it's a list of 2 elements and 3 elements. Then I can take that list of 2 and break it down until it's a list of 1 and 1. The convenient thing about being a list of 1 element is that it's already sorted, because there's nothing to compare it against. So what then I can do is take my lists that I know are already sorted and start merging them back together. And merging 2 lists that are already sorted really isn't that big of a deal, because I only have to compare the elements that are basically next in line, so in the first spot, and to build a new list that has the 2 already sorted lists together as one newly sorted list. And so this is what the merge sort does really, really well. Now to do it effectively, we kind of need 2 different functions here. One to merge 2 lists together, 2 what I'm assuming are already sorted lists. I called it left half and right half. And another method called the merge sort, which we'll call this method eventually after it has continuously broken down the lists until they're already sorted parts. So let's code the merge method first. So in the merge method, I've got a left half and a right half. What I need to do is come up with a resulting matrix, or not matrix, list, that is going to contain all the elements from the 2 merged halves. And so essentially what I want to do is say while the left len of the left half is greater than 0, and the len of the right half is greater than 0. What this proves to me is that both halves still have elements to attempt to merge together. And so if they do, then I need to start making some comparisons. So if the left half at, say, index 0 is, say, less than the right half at index 0, okay, what I want to do is insert the element from the left half into the result. So result dot append left half at 0. But what I want to do is pop it from it so that it comes off. Left half dot pop 0. And what the pop method will do is not only return the value that's at index 0, but also remove it from the left half matrix or from the left half list so I don't actually compare it again because I've already used it up. My goal is to kind of get rid of all the elements in left half and right half and build up a new matrix called, or new list called result. Now, if left half, the value at left half is not less than the value at right half, right, I want to do basically the same thing, but I want to append the value from right half at 0. Oops. And there we go. And we're going to keep doing that process until either right half or left half doesn't have any elements left. And I want to keep doing that because if they don't have any elements left, then if one of them doesn't have any elements left, then this comparison doesn't make a whole lot of sense. I'm going to get kind of what we call a null pointer exception. So here's the deal. Once one of them is completely empty, then I need to figure out, well, which one is empty, and I need to put all the elements from the other one into the result matrix. So I'm going to say something like this. If the len of left half, okay, is greater than 0, this would mean that left half still has elements in it. I want to take the result and make it equal to whatever the result was plus the left half. Okay, left half still has elements, so let's take what's in result and add left half to it and make it the new result. Okay, and otherwise, we're going to go result equals the result plus right half. And since left half and right half are already sorted, because we're assuming that they are, adding them to the end of the list is perfect because we already know it's completely sorted. Now this method needs to return result, right, and give it back to me so that I have these two merged lists together as one. All right, so now we have the ability to merge two items. Now it's time to get into the merge sort. So this is a recursive algorithm. A recursive algorithm always needs a way to kind of get out of itself. So essentially what we're doing is making a looping activity, but without like a counter or anything like that. What we're doing is making a looping activity based upon the fact that we can call the method that I'm in upon itself. So what I want to do first and foremost is identify my base case. And so if the len of my list, okay, is say less than or equal to 1, okay, so if there's one element or fewer in the list, I want to return my list. All right, that may seem a little ridiculous, but let's see how this is going to go next. The merge sort is all about trying to break down the lists. So what I'm going to do first, I'm going to go middle, okay, to identify what the middle element is or where the middle piece is. I'm going to go len of my list divided by 2. Okay, and so what that'll do is return the center index of the list. And what I want to do is make two different lists, a left list and a right list, which is equal to a slice of my list from the start to the middle. Okay, and I want to make a right list that is equal to a slice of my list from the middle to the end. And so this is me. I'm cutting the list in half. I have a left list and a right list now. That is a chunk of the overall list from the start to the middle and from the middle to the end. Okay? And so here's what I'm going to do that gets kind of weird. What I'm going to do is I'm going to apply this same algorithm, merge sort, to left list and right list. So I'm going to call merge sort on left list. And I'm going to call the merge sort on right list. Okay. And once I've completed those two, what I can do, once they're full and finished, I could return a new list that is the merged version of left list and right list. All right. And so let's come out and see how this all works. And let's go into our lists. So I'm going to come out and bring out the print statements. Let's make sure it works. Let's generate something on 10 elements. And let's do this. We want to do a merge sort, right? Oops, not a merge, but a merge sort on our list. All right. So let's see how that goes. And this should finish pretty quickly. Okay. And now let's beef it up onto 10,000 elements. Let's get rid of the print statements. And let's see. And you'll notice that all of our other sorting algorithms took about 8.5, 8.5, and 24 seconds. On 10,000 elements, this took almost a quarter of a second to perform. So although it may seem like it's a far more complicated algorithm, the fact that it never has to make a swap really helps improve its efficiency. And there are lots and lots of different algorithms like this: merge sorts, heap sorts, quick sorts, things of that nature, and you can look up all sorts of different sorting algorithms. The ones that don't make any swaps are by far more efficient. It's not to say that recursive methods are always more efficient than their iterative pairs. That's not what we're getting at here. But the fact that I didn't have to make any swaps really does help the efficiency quite a bit. So again, this isn't a sorting algorithm that I'm expecting you to be able to perform, but it is something that I wanted to demonstrate so that you can kind of see how it goes. I would highly suggest trying to code it out at least once so that you can see how it works out. But the algorithm itself it's a little complicated to get wrapped around your mind the first time through. So feel free to kind of look up some other resources or do what you want to do with it. But for the lab and the assignments, you will be expected to be able to work with a bubble sort, selection sort, and insertion sort. The merge sort is not something I'm going to require you to do. So that kind of ends it for our sorting demo. For the next video, we'll get into the searches, and that'll kind of lead us into this week's assignment. So we'll catch you in the next video.